Hello there. Let's continue plowing through some problems from chapter 16. 53 is another problem that requires the use of the bulk modulus. We're told that there's a cylinder 20 centimeters high, 10 centimeters in diameter, and it's filled with some kind of liquid. Here's a view of the cylinder from the side because we're told that the cylinder has a piston at the bottom, and the piston can be slid in and out, which would change the volume, of course, that the liquid occupies. We're supposed to figure out, based on some information that's given, how fast longitudinal sound waves would pass through the liquid. And so, since this is chapter 16, we're going to have to use this result. This is one of the formulas presented in the chapter. Much like the speed of a wave on a string, the speed of sound through a solid or liquid, if you're talking about longitudinal waves, depends on the bulk modulus and the volume mass density. So the mass is given. We're told that the mass of the liquid in the cylinder is 1.34 kilograms. What else are we told? The amount by which the piston is slid up the cylinder is 1 millimeter. Millimeter. A thousandth of a meter. And we're told that in doing so, the pressure inside increases by 41 atmospheres. Whoa. So I'll write that as delta P. This is the letter P, not the same, not to be confused with the Greek letter rho for density. So 41 atmospheres, and let's go ahead and convert that right now to the SI unit of pressure, which is newtons per square meter. So for every 1 atmosphere, there are 100,000 pascals, 1.01 times 10 to the 5th pascals. I just remembered as 100 kPa, kilopascals. Well, I guess I remember it both ways, don't I, since I just wrote that number down. Let's figure out what that increase in pressure is in SI. Okay, how many zeros am I working with there? 4.14 times 10 to the 6th pascals. That's a lot of extra pressure required just to squeeze this volume of fluid by 1 millimeter, starting from 20 centimeters. How are we supposed to figure out the bulk modulus? Well, you just use the definition. Remember, the bulk modulus is a measure of kind of the stiffness of your liquid or solid, how much extra pressure is required to produce a given fractional compression. It's the ratio of the change in pressure to what you might call the strain, the fractional change in volume. Now, your book does something clever, your solutions manual, they do everything all in one shot, one formula for the whole thing. They plug in the expression for the bulk modulus and the expression for mass density, and a couple things cancel. I think it's more illuminating to actually look at what this number is before we plug it in, so we can appreciate how large it is. Well, the volume here, I've written the letter A for area, and we know that the area is pi r squared. Well, let me remind you that pi r squared can be written as pi times 1/2 the diameter. Oops. Okay, I used a lowercase d there for diameter. The radius is half the diameter. When you square the quantity in parentheses, you get a factor of 1/4 out front, 1/4 pi d squared. I honestly find this easier to use because very often it's the diameter that's stated and not the radius. Same thing. So 1/4. Actually, I'm not even going to go that far at this point. Let me just say A times L. So I'm using capital L for the length of the cylinder. That's the 20 centimeters. I'll use capital D for diameter. But for now, let me just express the volume as the area of the base times height, because we're going to see that will make this expression a little simpler. The change in volume would be the volume swept out by the piston as you push it up by 1 millimeter. That would be the volume of this disc. So if you were looking down on the disc, it would also have a surface area or a base area of capital A and a height of DL. So the volume of that disc would be base times height, or A times DL. And now you can see why it's easier to just leave the volume and the change in volume in terms of A and L and DL, because all those factors of pi and diameter would cancel anyway. There's no need to write them. So delta V over V would be ADL over AL, and that's just DL over L. So we only have to, oh, I'm sorry, DL over L. So that simple expression for the fractional change in volume is a consequence of the shape of the cylinder. The diameter doesn't change. I guess that's the definition of a cylinder. In any case, let's evaluate delta V over V. That's the same as DL over L. Well, my L is expressed in centimeters. My DL is expressed in millimeters. I could convert both numbers to SI, but let's get some practice with those units. 1 millimeter is 1/10 of a centimeter. So I'll write that as 0.1 centimeters, and the denominator is 20 centimeters. And now I'm going to embarrass myself. Well, 1/20 is 0.05, right? And we have to divide that by 10, so 0.005. Let me check that. So 5 times 10 to the negative third, which you could call 5 parts per thousand. 10 to the negative third is thousandths. So we're changing the volume by 5 parts per thousand. What's the bulk modulus? Well, we just take the ratio of the required change in pressure to the change in volume. Now, here's an important point. The statement of the problem says that the pressure in the liquid increases by 41 atmospheres. Now, if you're thinking about this causally, you might be saying, well, the only reason the volume decreases is because we have to apply an extra pressure. We're applying pressure to the liquid, and as a result, the volume decreases. Well, whatever pressure you apply to the liquid, that same pressure exists within the liquid. And likely you haven't spent much time with fluid mechanics here at Long Beach City College, depending on who you took 3A with. So I'm going to use these arrows to represent the extra pressure applied to the piston. And just think about the piston in terms of Newton's laws. The net force on the piston needs to be 0 if it's in equilibrium. So the force exerted by the fluid would need to be the same. Pressure, P, is force per area. And since the surface area of the piston is the same on both sides, look at it this way. I've just argued that the force on both sides must be the same. The surface area, obviously, on both sides of the piston is the same. And that indicates that the pressure on both sides has to be the same. So that increase in pressure that you're applying is the same as the increase in pressure within the fluid. Those two things are equivalent. Okay, so now we can calculate the bulk modulus. And that minus sign, remember, is just to balance the fact that delta V is a negative quantity. So we'll just throw that away and deal with absolute values. This many extra pascals of pressure are required to produce that fractional change in volume. And notice it's dimensionless, meters over meters, centimeters over centimeters. And what do we get for the bulk modulus? Okay. Big number, 3, 6, nope. Okay, 3, 6, 8. 8.28 times 10 to the 8th pascals, which I think is smaller than a lot of typical bulk moduluses. But I'm going to go with it, and we'll see if we get the same answer that the solutions manual gets, because the solutions manual, like I said, just does it all in one shot. Now that we know the bulk modulus, the rest should be fairly easy. Let's calculate the mass density. We could do everything in steps like I've been doing. So the mass density, excuse me, is the mass of the liquid compared to its volume. And the volume is base times height, which is 1/4 pi d squared. That's the area of the base times the height L. And I'll do that all at once in my calculadora. Pi divided by 4. I really don't like the fact that I have to hit shift before I can access the pi button. What were they thinking? We use pi all the time. Pi divided by 4. If I was king, that's the first thing I'd fix. Times, what's the diameter? 10 centimeters. So that is 10 hundredths of a meter. I'll write that as 0.10, or 0.10 squared. Lastly, times the height of 0.20 meters. 20 centimeters is 20 hundredths of a meter. Okay, and I get a surprisingly small volume, 1.57 times 10 to the negative third. Well, remember, a cubic meter is actually a very large volume. Much bigger than a bottle of Pepsi, for instance. Okay, so we take, here's what I'll do. I'll be clever and put that number into memory, shift input on this calculator, and then I'll take the mass, which is 1.34 kilograms, and divide that by the volume, and I get that the mass density is 853, and that number looks correct because lots of liquids have densities around 1,000. 1,000, of course, is the density of water. Okay, most of the work's done. Let's see how fast these waves travel. Bulk modulus divided by mass density, then we take the square root. And I have to emphasize again, this only gives you the speed of longitudinal waves. Other types of waves can travel, well, I should say through solids. Transverse waves, not likely to travel through a liquid because you're lacking those shear forces. Don't forget to, oh, why does this calculator do that? Sometimes it'll just return the value 0 when I've clearly not been punching zeros in. Divided by 853. Okay. 985 meters per second. That's more than twice the speed of sound in air, and your solutions manual has 987. So I guess we're both correct if we agree. In order to do number 62, we have to introduce yet another quantity describing the elasticity of a material. This is a lot like the bulk modulus, but it applies to materials which are only stretched in one direction. So things like rods, wires. The bulk modulus deals with volume compression. So in a way, conceptually, this is almost a little easier. So here's a rod of some material. Maybe it's a steel rod. Horrible drawing here, but you've got a weight hanging. Think of these as, I don't know, wires or threads. You've got a weight hanging from the rod. It's very heavy, and you can imagine that if it's heavy enough, it may cause this to stretch just a little bit. And so let me indicate a tiny little stretch of the rod. This picture is misleading because if you actually had a rod this thick, it's not going to stretch because of, I don't know, I would imagine that this thing weighs, excuse me, probably as much as this thing does. So imagine this is more like a wire and you've hung an anvil from it, or a very large dumbbell, barbell. That makes it more believable. Something like, so a steel wire with a barbell hanging from it. That makes it more believable that this wire might stretch by just a little bit. But this picture will make it easier to motivate the formula here. Okay, so let's call the original length of this rod L, and then the stretch DL, just like before. That's a DL right there. And we'll introduce again this quantity strain. The strain of the rod is by definition the fractional change in length. That's not enough to indicate by how many millimeters it stretches. You want the number of millimeters compared to the original length. That's the fractional or relative increase in length. And we can make a couple of observations here. By the way, the weight hanging down here, let's say that the weight is the letter F. F for force of, obviously, if this thing weighs 100 pounds, then the downward pull on the rod is also 100 pounds. I think it's fairly clear that the strain, DL compared to L, should be proportional to how much weight you hang from the rod. Twice the weight down here should produce twice the strain, twice the fractional change in length. Now, that may not hold true as you hang larger and larger weights. Like if you hang 1,000,000 pounds compared to 1,000 pounds, you're probably not going to get 1,000 times the stretch, right? 1,000,000 is 1,000 times as great as 1,000. So if this proportionality were correct, absolutely, that would mean that 1,000,000 pounds should produce 1,000 times the stretch of 1,000 pounds. But of course, if you hang 1,000,000 pounds from just about anything, any kind of rod, it's going to break. So this law is only applicable for a limited range of weights. Okay, so that hopefully is clear. What else can we say? Well, what if this rod, instead of having cross-sectional area A, had twice the cross-sectional area? So just for definiteness, if we're talking about hanging 1,000 pounds from this rod, if the rod were actually twice as large in cross-sectional area, wow, it's just getting worse. You can imagine that it's not going to stretch as much, right? Obviously, if you hang the same weight from a larger diameter rod, it's not going to stretch as much because the weight is distributed over a larger cross-sectional area. So as the diameter of the rod goes up, the amount by which it stretches should go down. That's an inverse relationship. So the strain should be inversely proportional to the cross-sectional area. And these two statements can be combined into one. We can say that the strain is simultaneously proportional to the load hanging from the wire or the rod and inversely proportional to the cross-sectional area of the wire or rod. And we could just summarize that by saying that the strain is proportional to the stress. Stress could be defined as the force per area. It's not just how much weight is hanging from the rod, it's how much weight is there per square centimeter or square meter for SI units. Excuse me, because the larger the cross-sectional area is, the more spread out the force is, so to speak. And you'll notice the units here are newtons per square meter, which is the Pascal, but it's not really the same thing as pressure, is it? When you think of pressure, if you're applying a pressure to something, you kind of think of squeezing it inwards, but here we're talking about tending to stretch something or put it under tension. So I don't want to call it pressure. That's why we have this word, stress. How can we replace the statement of proportionality, the proportionality symbol, with an equal sign? We have to introduce a constant of proportionality. So the way it's done is, I have to pause and think about this for a moment. Oh, right. So think back to Hooke's law, where the spring force is proportional to the displacement. We'd like this law to have the same form. So here's the force-like term. If we just flip the two sides, we would have the stress on the left, just like here I've written spring force on the left, and we would have the strain on the right, and the strain is a lot like the stretch of a spring. So we'll say this: stress is equal to strain with some stiffness, so to speak, out front, some elastic quantity or some parameter that describes the elasticity of the material, and we use the letter capital Y. So it looks a lot like Hooke's law, and this is called Young's modulus, not the bulk modulus, but Young's modulus. And obviously, it's got to be related to the bulk modulus, because if you had like a cube of steel and you wanted to talk about how compressible it was, you would use the bulk modulus. If you had a long wire of steel and you wanted to talk about how easy it was to stretch it, then you would be talking about to stretch or compress it, then you would be talking about Young's modulus. I believe you could use this equation whether you were tending to stretch the rod or compress it. Okay, you could also write it this way, of course. Young's modulus is the amount of stress required to produce a given strain. And these are numbers that you can look up in tables. Many engineers have spent laborious hours of their lives measuring these things in laboratories, and we just have to look them up. That's what we're going to use for this problem. So we haven't even really started the problem yet, but now we're prepared to do so. Here's what the problem is really about. We're talking about the G string on a guitar. So this is not a bikini. This is a guitar string. Here's a close-up view of the string. Obviously, we're way zoomed in because guitar strings are pretty thin. We're told that the diameter of this steel string is less than 1 millimeter. It's less than half a millimeter. That's 0.46. We're told that every meter, that's over 3 feet, of string has a mass of 1.3 grams. That's G for grams, not 9.8 meters per second squared. We're told that when this string is properly tuned, it vibrates at this frequency, 196 hertz. Now, it's going to turn out that that's extraneous information. We don't actually need that number to solve the problem. Isn't that annoying when they do that? Because it confuses you, like, which of these numbers am I supposed to use? But that's life, right? I mean, in real life, I suppose you'd have not just one number that you don't need. There could be a whole bunch of numbers you're looking at that you don't actually need. We're told that waves on the string, when they're tuned to this frequency, will travel at 250 meters per second. Now, this is something that we will actually be able to show in the following chapter. We'll be able to connect the length of the string, the frequency, and the speed, but we're not there yet. So my advice, and you've probably learned this already in previous physics classes, if you don't know where to start, just start writing down formulas that you might use, like the speed on a string. We know that that goes like this. It depends on the tension and the mass density. Ooh, they gave us the mass density. So we're already partway there because we know the speed, we know the mass density. Maybe we're supposed to do something with the tension because we can obviously calculate the tension. Now, this is applicable to what type of wave? Because we just looked at longitudinal sound waves in a liquid, but now we're talking about guitar strings. That's transverse oscillations. This formula is for transverse waves on a string. Let's go ahead and solve right now for the tension in the string. Evidently, the required tension on this guitar string is determined by this speed, which they just gave us, and this mass density. Let's square both sides, solve for t, and it would be mu v squared. And I'll just evaluate that all at once. So the mass density, if I put that in SI units, I have to recognize that a gram is 1,000th of a kilogram. Remember, the kilogram is the SI unit of mass. So I like to call the gram a millikilogram because it's 1,000th of a kilogram. 1.3 thousandths. See that? 1.3 times 10 to the negative third kilograms per meter times 250 squared, and that will come out in SI units, 81 and a quarter newtons. Now, first of all, how do you set the tension on a guitar string? That's what the screws are for at the end of the neck, right? You turn the screws, it stretches the string, which of course increases the tension. And that's why we have to use Young's modulus. Let's see here. Young's modulus. What's the force being applied to the string? Well, that's really the tension, is it not? The force which exists within the string is the same as tension. That's kind of a subtle conceptual point. Let me kill more trees here. If this is the string, imagine just examining everything from here up. And maybe this part of the string, the steel string, or should I say wire? No, we don't call them guitar wires. That sounds silly. This part, let's say, is wrapped around the neck. You know how you turn the screw? I guess it's really wrapped around the screw. And so when we look at the force that's applied right here, well, tension we think of as existing throughout the string. So I could put a second imaginary line and apply Newton's second law to this little segment of the string. The force which is applied right here, let me get, where's the marker? The force applied on this side of that little segment would be the tension from the rest of the wire. And then the force here, well, that's the force coming from the screw. Those have to equal. So they're both equal to the tension. Have I convinced you of that? You could repeat that argument for any segment of the wire. If this little piece of wire is in equilibrium, then the tension on both sides must be the same. Okay, so the force that we're talking about when we look at Young's modulus is the tension that's established in the string. So since we're talking about a steel guitar string, we can look up the Young's modulus for steel. And what are they actually asking us? The statement of the problem is asking when the appropriate tension is established in the guitar string by twisting the screw, how much does the string stretch by? That's what we're trying to find out. We know that the string starts out at 75 centimeters. And that means we know what L is in the formula for Young's modulus. If we know what L is, we can look up Young's modulus for steel. We know what the tension is in the string. We just solved for that using the formula for the speed of a transverse wave on a string. The only missing ingredient here would be the cross-sectional area. That's how you calculate strain, right? You need how that force is distributed over the cross-sectional area of the string. What they're asking us for is the amount by which the string stretches. Okay, that's the one unknown here. And rather than, excuse me, it's that darn post-COVID cough. Rather than doing this all at once, like finding a formula in terms of pi and radius of the string and all that garbage, that's fine. You can do that. There's some advantages to that, but let's look at these quantities individually. So first we'll calculate the cross-sectional area of the string. Instead of pi r squared, I'll go with 1/4 pi d squared. Cross-sectional area of the string. And make sure you put everything in SI units. So 1/4 I'll write as 0.25 times pi times, now the diameter is 0.46 millimeters. So that's 0.46 times 10 to the negative third meters, right? 0.46 thousandths of a meter. Square that, and I get this really small number. I guess one disadvantage of doing it this way is rounding error. If I just write down that number and round it to a few digits, I'm losing some information there. It's better to round at the end. So how about I do this? I'll just put a blank line there to indicate I've calculated that. I'll put that into memory. And now I know that the stress, not the strain, the stress is the force per area, which becomes the tension over the area. So I'll take the tension of 81.25 newtons, and I'll divide that by the cross-sectional area. And now I have an expression for the stress. Again, I'm still introducing some error here. 4.889, I'll call it. That's a little compulsive. I don't need all those digits. 4.889 times 10 to the, what have I got there? 368. And that's newtons per square meter, just like Pascal's. And I'll put that number into memory now. Now, since I put it into memory, that means if I happen to write down the wrong power of 10, I'll still get it right when I use the calculator. And we need to look up the Young's modulus of steel. So I'm going to pretend that I'm looking it up in a table on the web or in the book, but what I'm really doing is just stealing it from the solutions manual. And they gave us Young's modulus as 20 times 10 to the 10th. That's a big number. It's not that big though, right? You can stretch a guitar string, no problemo. Whoops, off camera. Okay, there's Young's modulus. So I'm going to do this. I'll think of this equation as consisting of 1, 2, 3 quantities. I've already calculated the stress. I just looked up Young's modulus in a table on the web, right? And I'll solve for the strain, which is the fractional change in length. Let's kill another tree here. Okay, so dl over L, fractional change in length, which is what we call strain, is the stress divided by Young's modulus. The stress I have in memory, calculator memory. Now I'll divide that by 20 times 10 to the 10th. And I find that the fractional change in length is a number that seems reasonable, 2.44 times 10 to the negative third. So this guitar string will stretch by roughly 2.4 parts per thousand. So if it was a meter long, it would stretch by 2.44 millimeters. Well, it's not a meter long. It's 75 centimeters long. Did I write that number down? That was given to us. So here's an algebraic identity. Wouldn't DL be DL over L times L? See what I did there? The L's cancel. But the quantity in parentheses is the fractional change. So it changes by 2.4 parts per million. So we take 2.4 not per million, per thousand, 2.4 parts per thousand times the actual length of 75 centimeters. And I've still got this number in the calculator, so I'll multiply by 75. 75 centimeters, and I get 0.18 centimeters. But there are 10 millimeters in every centimeter. So we can write that as 1.8 millimeters. Sounds about right. That when you twist the screw to tune a guitar string, it's going to stretch by about that much. That seems reasonable. And a lot of you have probably experienced this. If you overstretch it, if you over tighten it, the guitar string will break. And that's kind of a different number from Young's modulus. Young's modulus tells you how much it stretches per stress. If you stress it too much, it just breaks. And there's a name for that quantity too, the stress that will actually break. I think that's called the tensile strength. Okay, now, as your solutions manual points out, it's not like the entire 75 centimeters is actually on the neck of the guitar. Some of that 75 centimeters is taken up around the screw. And the part that's actually free to vibrate from here to here, that's going to be a different length. And in the next chapter, we will learn how to calculate that length, given the speed on the wave, which is determined by the tension, and the frequency that we'd like it to produce. Remember, the frequency of vibration for a guitar string is what sets up the oscillations of the air around it. And that frequency determines the pitch that we perceive. So the whole point of turning the screw is to change the tension so that you change the wave speed, so that you change the wave frequency. And that's what determines the pitch. It's actually pretty awesome that we can explain, I don't want to say a majority of the physics of musical instruments, because there's probably a lot more that can be said, but some of the most important aspects of how musical instruments work, you will understand by your first exam. Let's skip ahead to an easy, fun one. This one requires the use of the formula for the Doppler effect as it pertains to electromagnetic waves. We're told that a distant galaxy has its light shifted, or its wavelengths shifted to greater values. So suppose this would be the wavelength of light emitted by some source in this galaxy if it were not moving away from us. In other words, if there was no relative motion between the Milky Way and this galaxy, but because the galaxy is in motion with respect to us, the wavelengths that we receive are longer than they would otherwise be. In fact, we're told that they're 0.5% longer, which means this drawing is obviously a gross exaggeration. I'm just trying to make it clear that the wavelengths are longer. So why am I calling it lambda minus if these wavelengths are longer? Well, remember, longer wavelengths correspond to lower frequencies because the speed of light is fixed as long as we're talking about light through a vacuum. And if you look at the fundamental relation for waves, the product of frequency and wavelength is always the wave speed. Now, in the case of light waves, we like to call that speed c, and it doesn't change. So the wavelength c over f. If the frequency has gone down, then the wavelength has gone up, and conversely. Okay, first let's translate this into math. Lambda minus is 0.5% longer. So you could say lambda minus is equal to the value of lambda naught plus another 0.5% of lambda naught. Now 0.5% means 0.5 per 100. 0.5 per 100 lambda naught. And of course, that means take the decimal point, move it 2 to the left. And we can also write this as lambda minus equals 1 plus 0.00. Am I doing this right? Yeah. 005 lambda naught. Some of you probably recognized immediately. You could just write that as lambda equals 1 plus 005 lambda naught. Another way of stating this in words is to say that lambda naught, the new wavelength from this moving galaxy is 5 parts per thousand longer than the unshifted wavelength. One of the questions you're being asked is, in which direction is the galaxy moving? Well, it's moving away. We know that light is red shifted. In other words, the frequencies are shifted towards the low end of the spectrum if the galaxy is moving away, and it's blue shifted, meaning the frequencies go higher if the galaxy is going towards you. Now, here's a subtlety not presented in the book. Pardon me. Here's the Milky Way, my Cinnabon Milky Way, and let's say way out at some distance is another Milky Way, another galaxy, smaller one maybe. It doesn't actually have to be moving directly away from us in order for us to observe a redshift. It could be doing something like this. If this is the direction of the galaxy's motion, then it would have a component in that direction. I'm so sorry. And a component in this direction. This is the direction, this is the component of the distant galaxy's velocity, which is responsible for the redshift. This does not contribute to the redshift because a galaxy moving perpendicular to the line of sight between our galaxies is not moving away or towards us. And it's much the same as the way police radar works. If this is a cop, a devious police officer setting a speed trap for you, so he or she is chilling on the side of the road, maybe under a freeway over a pass, and he's got his radar gun pointed, sending radio waves at you. If your car is moving this way, perpendicular to the cop's line of sight, he won't be able to detect your speeding because your car is moving neither towards him or away from him. There's got to be a component of your car's velocity that's parallel to the line of sight. And that's why you don't see police officers trying to catch you speeding by hanging out at the side. Let's say this is the road here and your car is going this way. You never see a cop pointing the radar gun like that. That's not going to work. If the car is in fact going in this direction, the cop would need to be like way down here pointing the radar gun that way. Okay, back to the problem at hand. All right. Let's do this perhaps the clumsy way first. Not clumsy, but unnecessary. Okay, lambda in terms of lambda naught. Remember the Doppler formula for E and M waves, or I should say EM waves, electromagnetic waves. There has to be a square root in there. There's a numerator and a denominator. And then we just use common sense to figure out whether there's a plus sign or minus sign upstairs and downstairs. And remember, I like to use the symbol U for light speed. It's the speed of the galaxy compared to the speed of light. And remember, this speed v is really the relative speed between our galaxy and this distant galaxy. But we can pretend that we're at rest and the galaxy is moving away from us. That's the speed v that we're talking about. Some books use beta. I'm avoiding beta here because we're already using beta for the decibel sound level scale. Okay, we know that the wavelength needs to be longer than lambda naught. So the numerator needs to be bigger than 1. The denominator needs to be less than 1. So we go with 1 plus u up top and 1 minus u downstairs. And all that's left to do is solve for u, because we know the value of lambda naught in terms of, or excuse me, the value of lambda minus in terms of lambda naught. We could plug that in here, cancel the lambda naughts. Let's go ahead and do that. So 1.005 lambda naught. The lambda naughts cancel. And we just have to solve this equation for u. Let's do that first, and then we'll go back and use the binomial approximation, because you'll notice this speed is pretty small compared to the speed of light, 5 parts per thousand. Oh, I just put the cart before the horse. The shift in wavelength is small compared to the original wavelength, and we're going to see that corresponds to a speed that's small compared to the speed of light. Okay, so I'll square both sides. 1.005 squared, and then the square root goes away. And let's just do some algebra. I'll move this to the other side. And let's get all the u's together. So if I distribute this, I really have a negative 1.005 squared times u. I'll move that u to the other side, and let me subtract this 1 from both sides. So when I distribute this to the 1, I get 1.005 squared. After I subtract the 1, I get this, and then I'll factor out the u on the right side. I've got this original u, and then 1 minus, actually plus, right? Since there's a minus sign here, when we move that u to the other side, that minus sign becomes a plus sign. I think I'm doing this right. All right, 1.005 squared minus 1 gives me, and this is kind of tedious because I have to carry all these digits around. How annoying. 1 plus 1.005 squared. So here I get 2.010025 times u. And I want to keep all those digits for now. So lastly, when I solve for u, I'm going to put this in the denominator here with my reciprocal button, and then I'll multiply by 0.010025, and I get that u is 4.9875 times 10 to the negative third. Can't we just round that? Let's just round that to 1 sig fig, especially because the percent change in the wavelength was only given to us with 2 sig figs. I'll just round it to 1 sig fig. So this is, well, maybe I shouldn't do that yet. I'll put this number in memory, because remember my definition. U is actually the speed of the galaxy with respect to us compared to the speed of light. So U is going roughly 5 parts per thousand, or the galaxy, I should say, is going roughly 5 parts per thousand as fast as the speed of light. And it's no coincidence that 5 parts per thousand is the same as 0.5%. So we will rework the problem more directly in just a minute. So V would be U times the speed of light. It's how fast it's going compared to the speed of light times the speed of light, right? Just take that ratio times C, U times, and the speed of light is not actually 3 times 10 to the 8th meters per second. It's something like 2.9979. So I'm just going to keep one significant digit. Take that ratio that I had in memory and multiply by 3 times 10 to the 8th. And were they asking for the speed in meters per second? Yes, they were. So I'll round that to 1.5 times 10 to the 6th. 3, 6. Yes. 1.5 times 10 to the 6th. Pretty darn fast. 1.5 million meters per second, or 1.5, what is it, 15? I give up. Let's just leave it in SI units. Okay, is there an easier way to do this? And by the way, wouldn't you say this answer is more meaningful really than this? I think to say it's going 5,000ths as fast as the speed of light kind of means more than 1.5 million. This number is so much greater than speeds we encounter on Earth. You know, if it was a number closer to 500 miles per hour, that would make sense because that's how fast some jets go, or maybe 1,000 miles per hour. But this speed is so much greater than that. At that point, you might as well just express it as a fraction of the speed of light because it has no relation to ordinary speeds. Let's go back and do this more simply, avoiding some of the carrying of digits that was tedious with that first method. So remember, if the light speed of a receding or approaching object is much less than 1, if the relative motion between the source and the receiver is significantly less than the speed of light, then you can say that the fractional change in frequency is roughly just that ratio. So if you're going 1% the speed of light, or if the galaxy is moving at 1% the speed of light away from us, then the fractional change in the frequency, the Doppler shift, is about 1%. What could be easier than that? And hopefully you were convinced that that's a really good approximation for low speeds in one of my previous presentations. Now, if it's a super tiny shift in frequency, like a fraction of a hertz or just a few hertz, then can't we just call that df? Instead of change in f, let's call it delta f with the special delta symbol, right? Lowercase d means teensy weensy tiny little delta f. And let's relate df to the change in lambda, because that's really what we're interested in, is the change in wavelength. We were given the change in wavelength as 5 parts per thousand, which is not infinitesimal, but it's pretty small. So I'll remind you that the wavelength is the speed of light divided by the frequency. And now let's use the magic of the calculus. Let's relate the differential of lambda to the differential of f, because differential really means tiny change. If the frequency changes by a little bit, how much does the wavelength correspondingly change by? So d lambda df, if we take the rate of change of wavelength with respect to frequency, this is not a calculus class, so I'm not going to go in detail here, but you can confirm that is the derivative. And so now let's move df to the other side. I'm treating the derivative like a fraction, like the ratio of two quantities. Both of those quantities are tiny changes. So when we take differentials, Chris Farley air quotes, we're really just taking the derivative and then moving one of the so-called differentials to the other side. This shows you how a change in frequency produces or relates to a change in wavelength. So if you know the wavelength you're currently at, excuse me, the frequency you're currently at, like 1 megahertz, you plug in the speed of light, you plug in your 1 megahertz, and then you plug in a tiny change in that frequency. Maybe you move away from 1 megahertz by 1 hertz, plug in that 1 hertz. And this formula will give you a pretty good estimate for how the wavelength changes in response. Okay, so what I'm interested in is the fractional change in wavelength. That's the change in wavelength compared to the wavelength we started out with. And this lambda really is lambda naught right now. So that's negative c over f squared df. This is d lambda times. Now I have to multiply by the reciprocal of wavelength. Well, the reciprocal of the wavelength would be the reciprocal of this quantity, So I multiply by F over C. And do you see how the C's cancel? This F cancels one of those F's. And we find that the fractional change in the wavelength is just equal to the fractional change in the frequency with a minus sign. And the minus sign is because if you increase the frequency, if df is a positive change, then the wavelength gets shorter. So d lambda would have to be a negative quantity. This is one of the fun things about calculus. It allows you to make simple estimates between the changes in two quantities. That's really what a derivative tells you, right? Okay, so we can go back up to here and recognize that if the relative speed, the so-called light speed, how fast the galaxy is moving compared to the speed of light, if that number is equal to the, or approximately equal to the fractional change in the frequency, then evidently it's also equal to the fractional change in wavelength. So here's another useful formula. As long as the relative speed you're talking about is much less than 1, relative, I mean, I guess that has two meanings, relative to the speed of light, but also its relative motion. As long as your light speed is much less than 1, the light speed in question, you can set the fractional change in wavelength basically equal to, it's really approximately equal to the light speed. So I've switched back to delta notation instead of d lambda. Same thing. It's got to be a small change in wavelength. So let's revisit this problem now and recognize that, okay, this is sort of circular logic here, but we can only use this formula if this is true. Well, supposing it is true, then these two would be roughly the same. And that means if one of them is 0.5%, the other one's 0.5%. 0.5%, again, is 5 parts per thousand. That's a pretty small number, right? That's much less than 1. So we're told that this quantity is much less than 1. And that kind of implies that this quantity is much less than 1, which is the condition that must be satisfied in order to use this equation. I think a better way to convince you that this works is to just compare the answers that we get in this method to what we did just a few minutes ago. All right, so this means that the light speed is roughly 5 parts per thousand, which is 0.005. Well, our more exact calculation where I kept all the digits, because this formula is exact. It's not like astronomers have some improved way of determining the speed based on the shift in wavelength. Not that I'm aware of. This is it. As far as I know, this is the formula. Now, you may be wondering, how in the heck do they measure the wavelength of light coming from distant stars? It's easier than you think, and you're going to know exactly how they do it in just a few weeks. That's one of the cool things we'll look at this semester, is how we can measure the wavelength of light in the field called spectroscopy. See how similar these are? Not much difference at all. In fact, the difference here, if we use the 7 to round that 8 to a 9, we've got 4.99 instead of 5. So the difference there would be 0.01. 0.01 compared to 5, I'll multiply by 100 to convert that into a percent. Okay, the error between these two numbers is 0.2%, 1/5 of 1%. So even for speeds as great as 0.5%, 0.5% the speed of light, that's still low enough that this approximation here is great. It's a very good approximation. I guess it depends on what your purpose is. If you're doing something really precise in astronomy, maybe that's not good enough. And what does it cost you anyway to use a computer for this formula? But for quick hand calculations here, nothing wrong with this formula. And let's add one layer to this problem by turning it inside out. Suppose now that you knew the speed of a galaxy. That's kind of backwards. Maybe I should be talking about radar instead. Now let's stick with a simpler example, because radar involves reflection, and then you would need to use a double Doppler shift. So instead of a galaxy moving away from the observer, what's with me in that word observer? Observer. Instead of the galaxy moving away from the observer, maybe it's somebody with a laser light moving away at some precisely measured speed. I want to show you what happens with this formula when you use it inside out, flipped inside out. So suppose the speed is a modest 30 meters per second. And that's away from the receiver of this light. I picked the example of like somebody in a vehicle with a laser light moving away from you because I don't think you're going to be measuring speeds of galaxies with this kind of precision. Find F negative if F naught equals, well, we'll go with 9.5 times 10 to the 14th hertz. I picked this frequency because this is in the visible range of frequencies, I believe. So if you've got a laser emitting light at this frequency, but the person holding that laser is moving away from you at 60 or 70 miles per hour, find the red shifted color of that light. Well, not color, I should say, the red shifted frequency. Okay. So since it's a red shift, that makes it easy to determine that the numerator needs to be smaller now. So we'll go with 1 minus u. Downstairs is 1 plus u. We can find u since we know what the speed of the vehicle is. And we can plug that in here. And if we do that directly, it's just kind of annoying. Let's see why. First, we'll calculate u. I'm running out of space here. Let's kill one more tree. U is the relative speed compared to the speed of light. So 30 divided by 3 times 10 to the 8th. Well, the 3's cancel, right? And that's 10 to the 1st divided by 10 to the 8th. So 10 to the negative 7th. Just in case, 30 divided by 3 times 10 to the 8th. 1 times 10 to the negative 7th. Okay. So if you clumsily just plug that into here for you, what are you going to get? 1 minus 1 times 10 to the negative 7th. 0. Okay, 999. I think I got all the 9s, 7 9s. And then downstairs we have 1 plus 1 times 10 to the negative 7th. 1.0000001. Okay, and I multiply all that by F naught. So let me do this quantity under the radical first. 0.9999999 divided by, I sound like a German, right? Doesn't that mean no in German? I sound like somebody in Germany yelling at their kid. 0.9999999 divided by 1.000001. Hit equals, take the square root. Okay, so it's 0.999999. Did I do that right? Check that. Okay, looks like I did. 3, 7 9s, got them all. Times the frequency of 9.5 times 10 to the 14th hertz. Okay, and I get this new frequency, which you'll notice is a little bit less than 9.5 times 10 to the 14th. So if I was asking for the change in frequency, if that's what the problem was asking for, I would have to take the new frequency and subtract the old frequency. Well, I just found the new frequency, so now I can subtract 9.5 times 10 to the 14th, and I get negative 9.5 times 10 to the 3, 6, 7, 10 to the 7th hertz, which sounds like a huge number, But compared to the original frequency, it's still very small, right? The shift in frequency in relative terms is still very small. Okay, is there a quicker way to answer this question? Of course there is. When your light speed is this darn small, I mean, that's really close to zero. Well, it's much less than one. So of course we can use this formula. The fractional shift in frequency is just very approximately equal to the light speed. So delta F would be U times F. All we have to do is take the light speed, that's the speed compared to light, and multiply it by the frequency, which is 9.5 times 10 to the 14th, and we get 9.5 times 10 to the 7th. There it is. So when applicable, save yourself some effort. Now, if you're going to use this, you probably want to include a little sentence that says, this approximation is valid because the light speed is much less than 1. This next one is kind of cool. For several of these problems, I've reminded you that the formula intensity equals power over r squared, that inverse square dependence, it's really only valid for an isotropic radiator where you don't have to worry about absorption and reflection. And of course, for sound waves, that's almost never true in real life. Most of the sounds you hear are produced near the ground or within a building, and there's all kinds of reflection and absorption going on. But this problem here is suggesting that there's an easy fix that's a fairly good approximation in a lot of situations, which is to assume that it may not be an inverse square dependence, but at the very least, the intensity is proportional to 1 over some other power of x. So as r increases, in other words, as your distance from the source increases, the intensity is still going down, but it may not go down as quickly as 1 over r squared. You got to figure if the intensity is not being lost in all directions and it is bouncing off of walls, maybe some of that power is being carried forward farther than it otherwise would, or maybe less so if the absorption is really significant. So there's two corrections. We're allowing for the possibility that the exponent is not -2, and we've got this coefficient out front. So we can take some supposedly real world data here, plot it, and try to do a best fit to figure out which value of C and which value of X would do the best job of correctly accounting for how the intensity drops off with distance. You can see here, as you get farther from the source, the intensity level goes down. So first, let's go into Desmos and plot this function and allow C and X to be parameters so that we can see how the curve depends on those two values. So I'll go with intensity equals, so the intensity is implied as the vertical coordinate here, C times, I'll go ahead and put the power P, that's the power of the source, over, okay, this is going to be really annoying. Remember in Desmos, I have to use the letter X for my horizontal coordinate. Well, the horizontal coordinate we're actually describing is R, the distance from the origin. And we're using the letter X as the exponent. That's unfortunate. So how about I go with X to the Y power? So my Y is actually the book's X, and my X here is actually the book's R. And they're not giving me the option to make these parameters. That's unfortunate. Why are they not doing that? Let me figure this out. Okay, it was because of the presence of that equal sign. Now they're giving me the option to make C a parameter, P a parameter. Okay, Y is not included as a parameter, so let me pick a different value. M? Okay, that works. So now I'm not going to use that because M represents slope, and we're interested in slope later. L. Okay. So once again, this lowercase c is the same as the lowercase c that they're using. It's the coefficient in front of power times x to the unknown power, or r to the unknown power. I'm using the letter x for the horizontal coordinate. That really should be r, the distance from the source. And the exponent, which they call x, the unknown power of r, I'm actually calling lowercase l. Make these all parameters. Okay, and obviously we're only interested in positive values of r, the distance from the origin. Let's see what happens if we change the coefficient out front, first of all. So that changes the shape of the dependence on distance by really just stretching the whole thing up or down. So a larger value of c would indicate that it takes longer for the intensity to decay with distance, and a lower value of c, the opposite. What about the actual power of the source? Well, as expected, actually it does the same thing that c does, doesn't it? So the one we're really interested in is L, that power of R in the denominator. So remember, we're modeling the intensity as being proportional to R to an unknown power, and that power is negative, or you could say 1 over R to an unknown power. So that's more interesting. Whoa. Higher values of L indicate that the sound drops off more quickly with distance. So the value of the exponent that we've been using is 2. That's the inverse square dependence. Now, maybe because of reflection, it takes longer for the sound to die off with distance, so that would make it look more like this. If the exponent were higher than 2, it would drop off even more quickly. So now let's look at the algebra. What we would like to do is turn this equation into an equation that has the form of the equation of a line, because then we can plot that line in Excel, do a best fit and extract information from that. So the best way to undo an exponential function, or to get rid of that exponent, is to take the log, right? An exponential function is like an anti-log. So we'll take the log base 10 of both sides, and I'm just going to write log. It's understood that I mean log base 10. And then let's use the rule for the log of a product. The log of AB is the same as the log of A plus the log of B. We've got a product of CP and R to the negative X. So that's the log of CP plus the log of R to the negative X. And next comes the step where we get rid of that, where we take the exponent out of the exponent. So we use this rule. The log of X to the Y, we can bring the exponent out front. That's Y times the log of X. And just as an example of that, the log base 10 of 10 to the 6th. Well, we know that the log base 10 of 10 to the 6th is 6, right? That's asking 10 to what power equals 10 to the 6th? Of course, it's the 6th power. Well, the rule says we bring the 6 out front, and that's 6 times the log base 10 of 10. Well, 10 to what power equals 10? The log base 10 of 10 is 1, so this is 6 times 1, or 6. So the rule works for that simple example. So we can write this as log of CP plus, it's actually a negative X, isn't it? We bring down the negative X, so minus X log of R. Now, I forgot to point out in the e-text, the table that's given, we're given the distances in one column and the decibel level. So the sound level in decibels in the other column. And what we have here is not quite the decibel level. We have the log of the intensity. So let's review the fact that the sound level is 10 decibels times the log of the intensity at any given distance compared to the so-called reference intensity. Now we use another rule for logarithms, which is the one that says, I'll do it right here, the log of the quotient, log of A over B, I'm sorry about the lighting here, that's the same as the log of A minus the log of B. It's a lot like this first rule. So we can split this log of a quotient into log of I minus log of I naught. So this is the definition of the sound level in decibels. There's no theory here. This is just the definition of sound level. But now we're postulating that perhaps the intensity has a particular dependence on distance. We're postulating this dependence on distance. And we put this in a different form right here. So now let's plug this expression for the log of I in here. All of this will now be substituted in there. Now, again, that doesn't necessarily make it true. We're trying to model a particular dependence of intensity on distance with this function. Okay, so I'm substituting log of Cp, where P is the power of the source, minus X log R, minus log of I naught. And lastly, we'll do as the solutions manual does and divide both sides of the equation by 10. So if you take the decibel level and then divide by 10 decibels, remember that business about like a loud sound could be 90 decibels. When you divide by 10 decibels, you get back to the number 9. Okay. And lastly, what are we doing here? Again, if we look at the data that we're given, we've got two data series. We have the distances from the source and their accompanying sound levels. So if we want to plot the data we've got on a line, we need to plot one of these versus the other. Well, it seems natural to think of distance as the independent variable and the resulting sound level as the dependent variable. So we would like to plot beta versus R or something similar to that. And you can see what we've got here is beta over 10 decibels and the log of R. So perhaps we can plot this quantity versus this quantity. And if we do that, we should actually have the equation of a line. Just to make that clear, this is the equation of a line in slope intercept form. Again, the letter X is doing double duty. If you're going to plot Y versus X, they have to have this relationship if they're going to plot as a line. So right now, our X is actually the log of R. You see how we don't have log of R squared or the sine of log of R or the cube root of log of R. This is just log of R to the first power. So if we identify the log of R with the horizontal coordinate, and if we identify beta over 10 with the vertical coordinate, then this equation does in fact have the form y equals, I'll call this y equals m. You see this unknown number out front? That's like the slope of the line. And this is like x. Some of you are being confused by the double use of the letter x here. So let me rewrite all of this one more way. Beta over 10 equals, and then plus log CP minus log of, oh, I'm sorry, I'm totally off screen there. Okay, what I've done is taken this equation and just collected the constants on the right side. And when I do that, this will be the horizontal coordinate that I plot. This will be the vertical coordinate that I plot. And so this looks like y equals mx plus b, because these are all constants. The constant power of the source, that coefficient out front, I naught is the reference intensity, that's just a constant. Excuse me. So my variables are the distance we are from the source, really the log of that distance, and the resulting sound level, really the sound level divided by 10. Hopefully you're familiar with this technique from previous classes, so I won't dwell on it any further. Let's go to a spreadsheet now, plug in the data that was given in the book, and see if we can determine the value of the slope of the line, which is really the unknown power of distance that we seek from the graph. I labeled some columns already. Let me enter the data that was given in the book. We're told the sequence of distances are 1 meter, 3 meters, 10 meters, 30 meters, and 100 meters. Can I zoom in? Let me zoom in a bit so these numbers look a little bigger on your screen. And then if I'd like to calculate the log base 10 of all those distances, I can just enter that formula once. So the log base 10 of this distance, I'll say log, and notice how a menu pops up. Let me scroll down to the option log base 10. I'll hit tab to select it. That's what you have to do in Excel. And then I click on that cell, hit enter. Okay, so the log base 10 of 1 is 0. We knew that. And now if I just double click in the lower right, it will iterate that calculation. So each of these is the logarithm base 10 of the number in the cell to the left. Then they gave us the sound level in decibels. So at 1 meter away from the source, the sound level is 100. You can see that the sound levels are all going down. But if you were to investigate this mathematically, you'd find that they are not going down according to the inverse square law. So this is not an isotropic radiator with uninhibited by reflections and absorption. Now this is a little silly. I could have just chopped off or divided each of these numbers by 10, move the decimal point 1 to the left, but I'll say equals this number divided by 10 and iterate that as well. And now it's time to plot this quantity versus this quantity. Because in my linearized, excuse me, in my linearized version of the equation, the equation that would actually plot as a line, this was my air quotes x coordinate, my horizontal coordinate, and this was my air quotes y coordinate. In this problem, we're using the letter x actually for the unknown exponent that we seek. So let me go up to insert a scatter chart without connecting the lines. And I'll right click, select some data. You know what? I got to get this stupid thing out of the way. Okay. Select data. I will add a data series. And for the series name, I'll say beta over 10 versus the log of R. Of course, that's a log base 10. So for my X values, they really mean horizontal values. That would be the log base 10 of my distances, the independent variable. And then consequently, what are the sound levels divided by 10? Okay, and I think I have to hit tab just to make sure that it recorded those changes. Hit OK, OK again. And sure enough, they do appear to fall on a line. So let's do a best fit line now. Right click on one of the data points, add a trend line. This is one way to do it. And I'd like a linear power, or excuse me, a linear dependence. That's already the default option. I would like to display the equation on the chart. Okay, so let me enlarge this font just a bit. And Excel is telling us that the slope of the line which best fits the data given to us is -1.5. So let's go back to the algebra now. Here was the equation we're dealing with. The slope that we're looking for is really supposed to be this. This is the unknown constant in front of our horizontal coordinate. So the slope equals -x. And the slope was given to us as, you carve out a last bit of space here, So the slope was given to us as negative 1.5. Evidently, that's negative x. In other words, x is 1.5. So our intensity does not fall off as 1 over r squared. With this data, it goes like this, 1 over r to the 1.5 power. So it drops off more slowly than the inverse square law. That must be because of reflections, or maybe this source of sound is focusing power in one direction. Again, it's like when you speak, you definitely have more of the sound power going forward away from your face than, away from the back of your head. I've saved the most difficult problem for last. This is number 69 from chapter 16. This is the one about a faraway star, which I believe is significantly brighter than our sun. And it's got a planet orbiting the star. And part B of the problem asks us to find the orbital radius for that planet, how far away the planet is from the star, based on some other information that they give us. That's the most challenging part of the problem. Part A is fairly straightforward. I've drawn two circles which represent spheres in these dashed white lines, because the first thing we'll be asked to do is to find the so-called surface flux, which is an astronomical term for the intensity of the electromagnetic waves leaving the surface of the star. That's an easy one because we assume the star is an isotropic radiator, which is probably a very valid assumption. We use the power and the radius of the star. It's just a straight up application of intensity equals power over 4 pi r squared. You take the total power output, that's the total number of joules per second leaving the surface of the star, and you distribute those joules per second over the spherical surface area, 4 pi r squared. So we'll do that first. Then we take a look at the planet, which is very far from the star. And of course, that first picture wasn't to scale. In actuality, planets are much smaller in comparison to the stars. And we have to imagine that the sun's rays, or the star's rays, I should say, are traveling this direction. They're all parallel. And even though they're striking the surface of the planet, some of them are coming in perpendicular to the surface. Some of them come in nearly parallel. So that angle changes as you move across the surface. All you have to do is imagine that that chunk of the planet is removed and just look at the light rays from the star which pass through this circle. So it's that circular cross section which intercepts the light. Just imagine looking at the planet in this direction and you would see the circular outline of the planet. Okay, so let's look at the numbers that are given to us in the problem. The problem statement includes the facts that the radius of the planet is double the radius of our planet Earth. So this fictitious or fictional planet is twice the diameter of our own planet. It also spins 3 times as fast. I'm using this symbol, the Greek letter omega, as the rotational speed of the planet. Earth takes 1 day to rotate, well, 24 hours roughly. And this rotational speed is 3 times that. So we can immediately turn that into information about the period of the planet. The period of the planet, well, if it's spinning 3 times as fast, doesn't it take 1/3 the amount of time to turn once? Earth turns every 24 hours. So this planet turns every 8 hours. And we might as well turn that into an SI quantity right now. So 8 hours times 3,600 seconds per hour, 28,800 seconds is the amount of time it takes that planet to turn once. Now, the total power output of the star is this enormous number, which is greater than our star's output. That's supposed to be a W for watts. And we're told that this star is ginormous in size. It's 6 times the radius of the sun. Now, of course, to get this radius and this radius in meters, we need to actually know the radius of the Earth and the sun. So you would look that up. This one I have memorized because I see it so often. Earth's radius at the equator is about 6,370 kilometers. This is the sun's radius in meters, 6.96 times 10 to the 8th. If you convert that into kilometers, you get this number, 696 thousand kilometers, which is more than 100 times of the radius of the Earth. Wow. So the sun is over 100 times in diameter that of the Earth, which would make it, let's see, 100 cubed. That would make it 1,000,000 times, more than 1,000,000 times the volume. You could fit more than 1,000,000 Earths inside the sun. Yikes. Let's start with the easy one, part A. What's the intensity at the star's surface? So for the inverse square law, isotropic radiator, it's easy. You just take the power and you distribute it over that spherical surface area. Well, the sphere that we're talking about is the sphere wrapping around the surface of the star. So that would be the radius of the star squared. Okay, here's the way I'm going to do it. Let me calculate r squared first, or really just r. So I know that the radius of the star is 6 times the radius of the sun. So I will take 6 times, in SI units, the sun's radius, that's our star, is 6.96 times 10 to the 8th. I hit equals. So now my calculator is displaying in meters the radius of that star. I'll square that. Then I'll multiply by 4 and by pi. So times 4 times pi. I hit equals. And then to put that in the denominator, I'll use my reciprocal button. And lastly, I multiply by the power output of the star. So this should really say power of the star. Uh-oh, did I hit multiplication yet? I think I did. Times 6.8 times 10 to the 29th watts. Huge number. In fact, it doesn't look right because I've seen these numbers in this solution already. Oh, that's the right number. We'll call this 3.1 times 10 to the 3, 6, 9. 3 billion watts. Wow. Well, check this out. 3 billion watts times your average microwave oven is a little more than, has a power output of a little more than 1,000 watts. I just checked mine yesterday. I think it's 1,200 watts on high. But I'll just round that down to 1,000 watts. So for one microwave oven, have you ever wondered why it's called a microondas, a microwave? It's because the electromagnetic waves bouncing around inside that oven are in what we call the microwave range. I think that's like a centimeter, maybe. The wavelength is about a centimeter. Okay, so just take this this third power of 10, subtract 3 from this exponent, and we're talking about 3 million microwave ovens. And I made a big blunder just a moment ago, didn't I? Intensity does not have units of watts. It has units of watts per square meter. It's the concentration of power in space. So every square meter, that's 3.3 feet by 3.3 feet, excuse me. Every square meter of surface on that star is emitting a power equivalent to 3 million microwave ovens. Can you even imagine that? Just standing in front of that 1 meter square patch and being irradiated with a power equivalent to 3 million microwave ovens. It really defies the imagination. Part B, like I said, is more challenging. The last bit of information they give us is the fact that each day, I say day because here on Earth, we think of a day as being 24 hours, but a day for this planet is how long it takes that planet to rotate once. And we know that that's only 8 hours. So during an 8-hour period, this planet receives this many joules of energy, not power, but energy from the star. That's how many joules are absorbed in the form of starlight. I don't want to say sunlight because we're not referring to our sun. This is their star. So you'll see why in a moment, but we would like to have the power, the rate at which energy is being absorbed by the planet rather than the total energy in a day. So the power received, E before I for that word, that's a weird one. Power received would be the total energy, let me just put REC for received, over the total time, right? wattage is joules per second, the total energy you consume or transform or whatever per unit time. So this is the number of joules of starlight absorbed, and that happens over an 8-hour period. And we'll multiply that by 3,600 seconds per hour. I guess this is where I could have just used the number that I already calculated, the number of seconds in a day on this planet, air quotes day, planet day, I suppose I could say. 9.4 times 10 to the 22nd divided by 8 divided by 3,600. And I get 3.26 times 10 to the 18th. Wow. Every second the planet absorbs that many joules. Okay. So now for the probably the most challenging part conceptually, let's go back to a drawing of that solar system. You've got the star here, and it's radiating energy in all directions. And as that energy moves outwards, it becomes less and less concentrated. In other words, the intensity drops like 1 over r squared. And way out here at this radius, and this radius here is what I called capital R orbit, to be consistent with your solutions manual. It's the radius of the planet's orbit around the star. That would be 1 year for the planet, planet year, probably different from our year. It takes our planet a little over 365 days to make it once around the sun. And I'll put the planet right here, and I will scale it up. Obviously, this is not to scale. The planet really is much smaller than the star. But I did that so that we can focus our attention on that circular cross section. So here's the, by the time the sun's or the star's rays get to the planet, they're all parallel, nearly parallel. Like it's impossible to practically to tell that they're not totally parallel. Any source of light that's very, very far away, by the time the light gets to the receiver, those rays are nearly parallel. Okay, well, intensity has units of watts per square meter. So intensity times area would be watts per square meter times square meters. The meters squared cancel and we just get watts. Now this isn't really an equation, is it? I'm just showing a relation between the units. And watts, of course, are the units of power. So I'm reminding you that power, if you have an area of arbitrary shape and you happen to know the intensity of the light striking that area, as long as that intensity is uniform throughout, take the intensity, multiply it by the total area, and that'll give you the total power impinging upon that area. This is cluttered now. Sorry, this little drawing is separate from my original drawing there. The reason I'm doing this is we can express the intensity out at this distance from the star by just taking the power coming out of the star and dividing it by the surface area of this giant imaginary sphere out at this radius. If we were to multiply that intensity by the radius of the circle here, or by the area of the circle, then we would have the total power, the number of joules per second intercepting this circle here. And is that the best way to do it? Let's see. The way your book does it is related. What they do is just observe that, according to this formula, for a fixed radius, the power is proportional to the area. Yeah, so just imagine setting up any arbitrary area on the surface of this giant imaginary sphere with the radius equal to the radius of this planet's orbit. Since the intensity is the same everywhere along this sphere, then if you were interested in calculating the power passing through any one of these, these areas that I just drew, you would just take the intensity and multiply it by that area. The bigger the area, the more power is passing through it. So for a fixed distance from the source, you have a fixed intensity. You can treat I as a constant, And that means that the power is merely proportional to the area, this statement right here. And if you understand that, then you can set up this ratio. You can say that oops, got to remember to check that I'm in frame here. The power received by the planet, remember that circular cross section is what tells you how much of the power is being intercepted. That power received to the total, that power received compared to the total power output of the star. Because remember, the total power coming out of the star is distributed over this ginormous imaginary sphere at radius r orbit. So the quantity of power intercepted by the planet compared to the total power coming out of the star, which is distributed over the entire sphere, that should be the same as the area of this circle, which is 4 pi times the radius of the planet squared. Oh, I'm sorry, not 4 pi, pi r squared. The area of a circle is pi r squared. You with me so far? So this radius right there is the radius of the planet compared to the total radius of the total surface area of this imaginary sphere at radius r orbit. So that would be the 4 pi r orbit squared. I'm able to set up this proportion or this ratio because of this statement of proportionality. Let me just go through that one more time. I'm saying that this area compared to the total area of this giant, enormous imaginary sphere, that ratio is the same as the power flowing through this circle, in other words, impinging on the planet, compared to the total power coming out of the star. Hopefully that's a reasonable statement to you. You can see that the factors of pi cancel. Did I really need to scribble that all the way out? Couldn't I have just done one line? Okay, well, haven't we already calculated this? We just did that right here because they told us how much energy the planet absorbs in one day, and we turned that into the amount of energy absorbed per second, which is power, joules per second. So we know this number. We just calculated it. They gave us this number. We can find this number, and we're looking for this number. Ah, yes. Remember, that was the whole point in part B. I hope I said this earlier. We're trying to find out how far this planet is from the star. Okay, so let's solve this for our planet. I mean, our orbit, the radius of the orbit. I'm not saying our planet. I'm saying capital R planet and capital R orbit. Here's what I get. Our planet squared over 4 times power of the star. Oh, I'm off frame again. Power of the star over power received. Okay, I just moved some stuff around, solved for the square of our orbit. Lastly, we would take the square root, and at this point, the steps I'm following are identical to the ones in your solutions manual. When we take the square root, our planet squared just turns into our planet. 4 turns into a 2. And here we'll have to put a radical sign. So the radius of the orbit of this planet around its host star is our planet over 2 root power put out by the star divided by power received by the star. And they're asking us at the end to express this distance, not in meters, because it's going to be a ginormous number that's inconvenient to use. Convert it into astronomical units. 1 astronomical unit is the average distance between Earth and Sun. Okay, rather than actually plug in our planet and divide by 2, we could just recognize, remember we were told that the planet's radius is double the Earth's radius. So half of the planet's radius would just be equal to the Earth's radius. So this number right here is 6,370 kilometers. I'll leave it in kilometers for now. And I'll go ahead and just compute this all at once on my calculator. We're told that the power output of the star is 6.8. That was in the problem, times 10 to the 29th. Okay, watts. And I divide that by the power received by the planet, which we already calculated. And that came out to be this number, 3.26 times 10 to the 18th watts. Hit equals. Then I take the square root sign. So I've got this number, 4.57 basically times 10 to the 10 to the 5th. Okay. So all told, we find that the radius of the orbit is 2.91 times 10 to the 369, 10 to the 9th kilometers. And then let me convert that into astronomical units. This is something you would have to look up. I've seen this number so many times, I have it also memorized. One astronomical unit is around 150 million kilometers. So 150 million kilometers. Now, if you had converted this radius into meters, you would have left this in meters. And then, of course, you'd have to enter the astronomical unit in meters as well after you looked it up in a table somewhere or just Googled it. GTS, 2.91 billion divided by 150 million gives us 19.4 kilometers, which, as your solutions manual points out, is about the distance between Uranus and the sun, or Uranus if you prefer. Tomato, tomato, turmeric, turmeric. Okay, so that was a challenging problem. If you think about it, it was really just repeated use of one or two formulas. The relationship between power, intensity, area, we used that several times. Like I said, I'm getting some bold gel pens in the mail, so it'll be easier to read my writing in the future.